welcome back. Today we're going to go through an application of differentiation. In fact, this is going to be a little bit of a deja vu time because we're going to go back to the limit concept again, especially when you have an indeterminate form, which could be 0 over 0, infinity over infinity, or 0 times infinity. We were trying to use algebraic tools to simplify the expression of the given function. In fact, we were using a simpler version of the function and then passed a limit for that simplified version of the function. If you have trigonometric or transcendental functions in the expression of the limit, then most probably, algebraic techniques will fail to apply or simplify the given expression. So we need a more advanced tool to take care of those indeterminate forms. So for that reason, I'm going to introduce you what's called L'Hopital's rule to take care of certain indeterminate forms. The very immediate application is to handle the limits of the form 0 over 0 or infinity over infinity or 0 times infinity. So let me just go ahead and then bring up the description of the L'Hopital's rule, and then we can sort of like start moving from there. All right, here is the description of the L'Hopital's rule. As you see that we're trying to find this limit of the quotient f and g as x approaches c. And possibly this is the one producing 0 over 0 type indeterminate form. And what we want from f and g is that they should be differentiable on an open interval, AB, that possibly contains c somewhere. C is the limit point as you see here. And also we want g prime to be non-zero for all x except c. All right, so we're not dividing by 0. So then this limit that spits out 0 over 0 type indeterminate form is equivalent to the limit of the top divided by bottom, but here as you see that the top is the derivative of this top here, so this is f prime, and then this bottom here is a derivative of the bottom g here. So in other words, when you have an indeterminate form in the form of a 0 over 0, then you can actually look at the individual derivatives of the top and the bottom, and then that's a brand new quotient, and then you can pass the limit for this brand new quotient, and if the limit exists, then the limit of the original function, which is f over g, is the same as the limit of f prime over g prime as x approaches c. And the good news here is that this is not just applicable to 0 over 0 type indeterminate forms, but it is also applicable to infinity over infinity, or minus infinity over infinity, infinity or minus infinity divided by minus infinity, or minus infinity divided by minus infinity. As I said, so the top may converge to infinity, the bottom may converge to infinity, or minus infinity, all sorts of combinations. Then you can still apply this kind of like idea to say that this limit is exactly equal to the limit of the top derivative and the bottom derivative at the same limit point. Going back to the exercises here, you can see all different combinations of indeterminate forms. In fact, you have 0 over 0 here, I'll explain that. And this is infinity over infinity. And this one is not one of those forms, in fact, that is listed in the L'Hopital's rule, but we're going to use a little algebra to tweak this and make it look like either 0 over 0 or infinity so that we can use the power of the L'Hopital's rule. Because when we were talking about limits earlier, in early chapters, we just had the algebra tools to take care of those limits, but nothing else. So now you have the power of differentiation because we take the derivative of the top, derivative of the bottom. It's a quick operation as long as you know how to take the derivatives. And then you pass the limit for a brand new function, and that if that limit exists, then you're done. So this is like a quick detour of all the stuff that we learned earlier, and it's sort of like a fast track of finding limits where you have indeterminate forms. So why don't we consider part A to start with? So as you see that I have sine 5x divided by tangent 9x, and x approaches 0. So what we do in general is just a function evaluation to start with. So we're just going to plug in 0 here. So this becomes sine 0 and tangent 0. So sine 0 divided by tan 0. You can just use your calculator and make sure that it's set to the radian mode, and then you will see that this is almost like 0 over 0. So you should probably evaluate those individually, because if you type in sine 0 divided by tan 0, probably your calculator is going to give you an error. But we know that sine of 0 is 0, tan of 0 is 0, so you're in the form which we call an indeterminate form. So now we need to find an interval where these functions are differentiable on, and hopefully the bottom function is not 0 at anywhere in this interval except the limit point x equals 0. So staring at the function sine 5x and tan 9x, I know for sure that sine is differentiable for all x, so we don't have any problem finding an interval containing 0 for this function. But for tan, we got to be cautious, because normally tangent x function has vertical asymptotes at pi over 2 and minus pi over 2. And specifically speaking, this is tan 9x. So that the interval that we're looking for should not contain beyond minus pi over 18 and pi over 18. Because when you plug in this endpoint here for tan, that's going to be tan pi over 2, which is undefined. And this is going to be tan minus pi over 2 when you plug in. So that's also undefined. But anywhere in between negative pi over 18 and pi over 18, we should be safe. And that also contains the limit point 0. Even though the tan function is 0 at that point, that's okay, because tan is non-zero on this interval. You can actually graphically check that tan is non-zero on that interval. So once we sort of like spot this interval, so we can go ahead and apply the L'Hopital's rule, which essentially states that this limit is equivalent to sine 5x prime, the derivative of the top, divided by the derivative of the bottom. Okay, so this is tan 9x prime. Okay? All right. So then let's just find the individual derivatives. We should probably utilize the chain rule to take the derivative of this, because you have the outer function sine, inner function 5x. So the derivative of this is what? The derivative of the outer function, which is cosine 5x, times the derivative of the inner function, which is 5. Okay? So that takes care of the top. And for the bottom, we're going to apply the same strategy. This time the outer function is tan, and the inner function is 9x. But we know that tan has the derivative secant. So secant squared 9x times the derivative of the inner function, which is also 9, right? 9x has the derivative 9. So essentially what we did here is that after we apply the L'Hopital's rule, okay, L'Hopital's rule here, after we apply the L'Hopital's rule here, that we just said that this limit, which was originally 0 over 0, is the same as this limit. So what we're going to now check is what this limit spits out. All right, so x approaches 0, so I'm going to do function evaluation right away. So this is cosine 0 times 5, and secant 0 times 9. And you can use your TI-84 to find those values. In fact, cosine 0 is 1, so the top is going to be 5. Secant 0 is still 1. You multiply it by 9, so this limit turns out to be 5 over 9. Since this limit exists, I can go ahead and then say that this limit here is exactly equal to 5 over 9. And this is the graphical outlook of the function sine 5x divided by tan 9x, and we were talking about the limit at 0. I can perfectly see from here that regardless of where you approach 0 for x, the corresponding function values would approach somewhere. At least we know that it's finite. So to see exactly where the values approach, I should probably zoom in. Even though this is like -1 and 1, I have to zoom in more to see what those points are. This is me restricting y min and y max. So I chose my y min to be 0 and y max to be 1, so that I can perfectly see where the corresponding function values approach, as you see. So if you sort of like walk all the way on this curve here, right, you approach this number, and I know exactly what that number is because I found it. So that number is 5/9. And similarly, if you approach 0 from the left, that means you're walking all the way on the curve in this direction. So you're going to approach 5/9. So the graphical outlooks are always powerful in terms of verifying your work. And then in this case, I verified that the limit is 5/.